Meanwhile, I'm going to, because, last talk of the day, short day, interrupted with a bunch of stuff, so super exciting. But who here is ready to talk about JavaScript? Woo! Yes! Last talk of the day, so we're going to do a lot of code. We're not actually going to write any code, it's going to be on the screen. So that's, of course, a big no-no, and so, of course, that's what I'm going to do. So let's take a look at this here. So what we're actually talking about is revealing your intent. This is what you're really trying to do. So we're not going to look at TypeScript, we're not going to look at PureScript, we're not going to look at ClojureScript. We're going to actually look at JavaScript and how we can reveal intent with JavaScript. So what we're going to cover types and type definitions. We might kind of hustle through some of them, and I'll kind of do a quick spot check and say, like, how are you guys feeling about this? And we might just kind of zip through some of the explanation. We will take a look at predicates as types. We're going to take a look at subsets and subtypes and how they relate. We're going to look at higher kinded types, and we're going to look at building a domain model. All of this with the idea in mind that we're going to tell other people and our future selves what we meant. So, a little bit of administrative minutia. This is the stuff that I use to do this. It's no joke. There's no special magic ES6 stuff happening. I did use a library that I wrote, and I'm actually running code live. So when you see code output, it's intentionally set up with a timeout, so it's gonna print out a little slower, so you kind of get this feeling like, hey, it's actually running. But no, really under the hood, it's actually running. That's really important because you'll be seeing output and it's not, hey, here's a sneaky slide, and I promise you that it works. It really does work. So, my slides are available online. They're available here. They're available on the LambdaConf or in the LambdaConf repo. And they're recording right now, so it'll also be available as a video later. So feel free, sit back, take it easy, enjoy the ride. So I'm Chris. This is me. This is how you find me. These are the two best ways. You can find me on my website, and there's all kinds of contact information there. You can also find me on Twitter. I respond just like that. Sometimes I do. So I'm a JavaScript programmer. It's not the only thing I do. I write in Scala, I write in Clojure, I write in Bracket, I write a bunch of different stuff. I write in a variety of different languages, let's say that. But most of the time, when I'm at work, I'm writing JavaScript. And I'm writing it functionally, because functional, right? I'm a math geek. I have a degree in math, I love math, I read math texts. This is what I do. It's kind of just part of me. So when I discovered functional programming, I was like, oh, this is awesome. Math, it's great. And I'm a tool builder. I don't really like living in the UI. That's kind of where JavaScript started from. But really, I like living somewhere between the UI and the data layer. The HTTP requests, the stuff that's like the business logic in the front. That's the kind of stuff that I like, and I really, really like solving problems with tools. So I build a lot of them. So let's talk about the gorilla in the room, huh? Coco. JavaScript. JavaScript is ubiquitous at this point. It's something where, you really want to say, it's fluff, it's going to go away. Sadly, or happily, I don't know, for me it's happily because it keeps me employed. But sadly, it's not really going anywhere. So we have to find a better way to actually work with it. So, fact, writing and maintaining large JavaScript applications is really, really hard. And there's a reason for this. The reason for this is, one, the code gets messy, and two, it's very hard to go back and discover what you meant before. So, let's take a look at this list here. No required build step. You don't get a guarantee. Unless you're using TypeScript, unless you're using PureScript, unless you're using Elm, you don't get a build step necessarily. You could, but you don't necessarily. Remembering where things is tough, or remembering where things are is tough. When you start digging into the code, did I leave it here, or did I put it over there, or the file's named wrong? That happens a lot. And remembering an old function contract is impossible. The bigger the code base gets, the harder it is to remember what that one thing that you wrote that one time does. So, let's take a look at how we solve this. Let's look at typing. JavaScript isn't really untyped. It's not like, oh, well, we've got some set of stuff and there's no promise. It's typed, it's just singly typed. That type is dynamic. So really everything's an object, and that's kind of like the JavaScript IO kind of sort of like small talky thing, right? Everything's an object, but really it's dynamic. So if we were to write a function, it would look like this. This is a demonstration of what the what dynamic scripting gets you. So we have this vector add function. It takes in two vectors, it adds them together, it assumes that it has 3 values in each, and you get stuff back. So we're going to try adding 2 arrays of numbers, which is what we actually wanted to do, 1 array of 4 elements, 1 of 3, and a couple of strings, because why not? And so just to get an example, we'll actually run this code, and you can see the first one works normally. The second one acts real weird because it just ignores that one. So what happened to the other element? And the last one, yeah, it took those strings and it actually created an array with strings kind of jammed together. This is not what we meant to do. So what if we were to just put in naive type checking? We were to just say, you know what? All we really want to do is just throw an error if there's an array, if it's not an array. You know, that's kind of the JavaScripty, like, I'm going to throw a bunch of conditions at it and hope that I catch all the stuff. And so I created this little function. It's really, really boring, and it just says throw an array mismatch. And it literally just says, is it an array? No, this is an error. So there's nothing magic under the hood. And if we run that, then we get an array as output for the first one, an array as output for the second one, and an error on the third one. Because the third one is a string and it's not an array, and so that's better than nothing. Now, the important thing is functions are data too. And this is not like the functional programming, hey, functions are data, first class citizen. No, I mean like they're objects. Like you can actually manipulate the object. So, did that run away from me? I think I reordered this wrong. I'll talk real quick. So just to catch up, so you can basically attach things to it. But more important than that, with that data, we can actually type it. So functions are typed like this, right? You have a type coming in, you have a type coming out. This is like if you write in Haskell, if you write in Scala, if you write in any strongly typed language, any statically typed language, you're already familiar with kind of how this looks. Right? And so then you can start doing kind of this fun typing game where it's like, oh, well, I have this X and it's typed A, and so then f of X is typed B, and I have this value, and it evaluates that way. This is kind of how we can look at functions. This is going to be really useful coming up here soon. So, going back to revealing intent. Functions as objects, we can actually attach metadata to our functions. This is when you play that prototype game, it's like, oh, I'm going to add things to my prototype, and stop that. I know that you want me to connect to the network, and I really don't want to. So you can attach things to a prototype and instantiate the object and all that good stuff. Well, as it turns out, you can use that for good as well as evil. So what we're going to do is exactly that. We're going to declare what our type is as a string and just attach it. Just jam it right onto the function and say, here I am. And this is what you get. Here's my vector add function. Now I'm telling you what it does. You can actually say, hey, what do you do? And it'll tell you. And it still throws on array mismatch. So if we run this code, you'll see I've got an extra function here that just says, what's your signature? Tell me about yourself. And when we run that, we get our signature, array, output's an array. We get 2 arrays as output, and then that final error that we expected to have thrown. Now, we can do better than this. We don't have to simply say, oh, well, we're going to jam stuff in and jam stuff on, and hopefully this is all going to work out for the best. Instead, we got this nifty library. It's called SIGNET. I can say, I want to enforce my function. and I want to enforce this typing. I want to be able to say, I have 2 arrays coming in, it's going to output an array, and this is the function that we're going to enforce. So do that. And now we're going to run exactly the same functions we ran before. Remember, this is live code. This is not hocus pocus. There's actually code happening under the hood here that's really doing this. We're getting the same output. We're still getting, you take 2 arrays in, you return 1 array, here's the output from the operations on the arrays that we can work with, and here's the error for the one that fails. So now we have something we can work with. This gives us a lot more flexibility in what we need to do, and it reduces the amount of overhead. You don't have to think about, well, did I write this function to properly fail when the type is wrong, that kind of thing. That goes away. Now we can actually really worry about what our intent is, and we can just state it and move forward. Now, what we have to do in order to make this work is we have to start thinking about types as predicates. We'll address that in just a second. So if we look at this as functions as a mapping mechanism. So functions provide a way to map one set to another. And predicate functions will map whatever set they take in to a Boolean, right? So it's going to end up looking like this. We could actually define some function phi that's going to map A to B when our predicate P is true, when we take P of X, and false, it goes to the inverse of B, right? So we can actually kind of do this type to set mapping. It gives us some nice wiggle room in there. I know that philosophically there's a difference between a set and a type, but for the argument here, this works. And we'll see that in just a second. It's really handy. So, a type can be considered as a set to which values belong. This means that we can actually use that to start defining our sets. So a type set can actually be defined as a predicate function. And this arises from the Curry-Howard isomorphism. If you're not familiar with it, you should go check it out. It's really fundamental and important to kind of the way that type systems work today and the way that programming works today. So it's a little abstract, but it's definitely well worth at least being familiar with it. I'm not going to go into it now, but I wanted to kind of bring that up. So if we start kind of going through this, we've got native types are named sets, right? And we can name them off like this. We've got string, number, object, array. Actually, array is really just an object that's kind of magical. But what if we had types that looked more like this? We can actually extend this with predicates and say, I want an int or a tuple or a natural number, an age. I want a vector. I want something other than just kind of the built-in types for JavaScript. This is what I really want. So I created this utility function, and I wanted to show it here just because all this is really doing is it's just saying, hey, I'm going to check the type and throw an error if the type is wrong. I'm doing this because otherwise the SIGNET type checker just returns true or false, and that's not going to be particularly useful for actually demonstrating what's happening. But if we take a look at something simple, let's say we wanted to create a lowercase type. So it's a string, but more important than just being a string, it has to be a lowercase string. So, stop that. Good Lord. Okay, so our lowercase string, we can actually test it pretty easily, right? It has to be a string. And if we take the value to lowercase and it's the same as the value, then we'll accept that as being a lowercase string. That may be a little hinky, but it works for demonstration. So now if we take a look at this, we've got foo, it's all lowercase. We've got bar, and that's all lowercase. And we've got baz, and it's kind of wonky, right? So in theory, then, when we check the types on this, we should see 2 passes and 1 failure. And that's exactly what we get. So all of a sudden now, predicate functions map to type signatures, map to meaningful output, something that we can actually say to our user and tell them what we meant. This is really important. So, type polymorphism. Yes? Anybody? No? Okay, I see a couple nods. I'll do kind of whirlwind tour. This is not like your class polymorphism stuff. This is, I've got a type and I want to subtype it and I want to subtype on that, and this is working from the base types of JavaScript. So we can actually define our subtype within this scheme as a subset of another type, right? So we're considering our type as a set, so we're going to take our subset and call that our subtype. So a subset could be inclusive of the same thing. We could literally just give it another name, right? And that would be like type aliasing. So we can say we've got a number, right? This is a base JavaScript type. From there, we're going to define an int. So that restricts it a little bit. So now we're only taking certain numbers. From there, we can say, okay, well, I really only want the natural numbers. So this is actually only 0 in the positives. And finally, I want to define an age. So this is where we start getting into actually declaring something meaningful for ourselves and the people that are going to be looking at our program in the future. When you see age, you don't think, oh, I wonder what that looks like. You know what it looks like. It's a number. It's going to be greater than 0. It's going to be incremental through the integers, and it's going to stop at some maximum number. So this is actually something that means something to us and other people. This is great. So this is what it would look like. Here is our number being subtyped as an int, and we can check our int just saying if our value is the same as the floor of that value, then we know that it has to be an integer. Our natural numbers are going to be any integers, which are greater than or equal to 0. And our ages are going to be anything that's going to be a natural number and less than 150, right? So I don't know of anybody that's actually lived greater than 150 years. I don't know, Methuselah. That's about all I've got. So let's use this. Let's take a look at actually what happens. By the way, don't mind the syntax highlighting. It has a couple of janky little problems. The plugin it's almost there. This is not something I wrote, so I'm not taking any claim on it. I'm just saying I apologize if anything looks a little wonky. So we've got an int check for 3.2, -3. We've got a natural check. You know, we've got these various different checks down, and we expect to see fail, pass, as I kind of go down the road here. So this is a pass. This should be a fail, and this should be a pass. So we should actually see 3 fails, 3 passes, and we should be in good shape, right? And there they are. And all you had to do was just say, this is my original set, this is my subset, this is the subset of that, and this is the subset of that. So at any point, an age is always, this adheres to that nice Liskov substitution principle where you can actually say any age is a natural number. Any natural number is an int, and any int is a number. So we can actually plug an age in for anything that requires a number, and it works, right? There's nothing that would stop us from basically performing the same actions. We have that correct behavior all the way up the stack. Now, let's take a look at higher kind of types. How many of you know what a higher kind of type is? You're familiar with it, comfortable with it? Okay, so I'll try to be really brief on this. So if we define a higher kind of type, it's basically just a type, and I'm going to talk and then I'm just going to like zip, zip, zip. It's basically a type that accepts another type before it's finally fully defined. So it's kind of related to partial application, currying, and what have you. So if we were to take a look at this, it's going to be a data type. It's related to currying and partial application, and the signature looks kind of like this, where you can say, okay, I've got this thing. It takes a type, it outputs a type, and then that results in another type. So this is kind of the high level, like 10,000 foot level of a higher kind of type. So let's take a look at a tuple. A tuple is a great example of a higher kind of type because anybody that's worked in C# or Java or anything, any of the old school languages or any of the new school languages that are using static typing that are supporting higher kind of types, you're going to see this kind of thing because tuples are very popular, right? So a tuple is going to look like this. We have a tuple. We can say it's a number, and and ultimately we're going to call that a point. That seems like a fairly reasonable thing to do. You get the Cartesian coordinate system, and you've got a point there, and it takes a number and a number. So if we take a look at that, this is what the tuple type looks like. Hooray! It's a little longer than the others, but nonetheless, it has a little more checking to do. It has to make sure that all the types line up. It has to make sure they're in the right order. Everything has to kind of line up right. Now let's actually use this thing. So we've got a subtype, and we're going to call it name. And we're going to create first we're going to test first our tuple with number. The next test is going to be with an age and a name. So we defined our age before. Now we're defining a name. So we're going to make sure that 21 Bobby actually matches. And we're going to try age, name, and we're going to pass in a couple of numbers. And let's see what actually happens with this. So we can see that it's actually correctly checking your number, your name, your age. Everything is lining up correctly. We're actually getting what we're expecting. And all we had to do was say, this is what a tuple generally looks like, and insert it into the library and say, this is how you work with this. Go. And from there on, you actually just get it. And it works. It comes together. And this is precisely the kind of thing that we want to get to, because this gives us the full range of motion when we're talking about providing information to the people that are going to be using our code and writing against APIs that we've developed already. So this is what we want. Pardon me. Now, let's actually take a look at really revealing intent. It took all of that to get to this, because now we can say something about our domain. What does our domain look like? Well, let's say we have a string, right, base type, and we want to create some higher kind of type, let's say formatted string. That formatted string takes this regex. You're going to have to trust me on it. It matches your standard social security number with dashes and all. And so we're going to call it an SSN. So once again, we're at this place where we can say, this is the kind of type that it is. This is what we want to call it so people know what it means. And if we use that, rather this is the definition for your formatted string. And if we use that, we can actually test our various different numbers and see what we get. Our first one is a valid SSN with the dashes and all. The second one is the correct set of numbers, but it's missing the dashes, so it doesn't actually conform. And the third one is just way out. So we should only get one pass, and we do. So this is something where now we're getting errors on the various different kinds of data that we want. We're checking against regex, we're checking against base types, we're verifying all the kinds of things that we really want to know about our data. But in the end, what we're really saying to all of our users and ourselves in the future is, this is what you meant when you wrote this. This is what you intended to have happen. So when you do it wrong, rather than having to go rifle through all of your dynamic code, you can now say, oh, I called that endpoint and it didn't work right. This is why. It really wanted one of these and I gave it one of those. Of course that's not going to work. We get the benefits that you get from your strongly statically typed languages, but without having the overhead of always having to do it. So if you're inside of your module and you've got that all wrapped up and you're just kind of pulling stuff out and saying, oh, well, this is this little function here and that's that little function there, that's fine. You wrap up your API endpoints, you say, this is what I do. And your user will understand. They'll know what this means. So everything old is new again. Let's go back and actually take a look at our vector addition function that we started with. We're going to use SIGNET. We're going to enforce the function, and we're going to say it takes in two 3D vectors, and it returns a 3D vector. And as you can see, we're just aliasing it. We're not even doing anything magical. At this point, we're not writing a predicate anymore. We've already done all the work. All we have to do is say, this is how you define what a 3D vector means. And we can say right here, it takes in two 3D vectors and it returns a new 3D vector. When we run this code, now this one is two 3D vectors. This one has an array of length 4, and this one is strings. So we're going to see that for the first time, we actually tell people what we intended to do. And this is why types are so important. And this is why we can really convey important messages through simply typing endpoints that people are going to touch when you're working in JavaScript. You don't have to type everything. I would encourage you not to, simply because it's going to, at times, inhibit your flow. And it ruins that dynamic flavor that people love about JavaScript. People love about Racket. I'm a Racket lover. And there's something about dynamic programming that sometimes it's just like, oh, this just feels awesome because I'm not worrying about, I know what the types are in and I know what the types are out, and it's right here and it's isolated and it's closed within this particular scope, and so nobody can touch it anyway. I just want to write the code. And sometimes I want to say, no, this is important to understand, and this gives us the ability to do that. So, what does it all mean? Types add guarantees and add reference information. They tell your user what you mean. They guarantee correctness on input. They guarantee correctness on output. They provide easy inline reference. At the beginning, we looked at actually capturing that signature data. That signature data is always available in the function, so you can pull it back later and say, what did I really mean? What does this actually mean to me? You don't have to go rifling through the code because it's right there in front of you. And it's easy to access. Finally, it gives lasting notes for anybody that comes in the future. So, the other thing that we get, and this is something where this is not a ding against TypeScript or PureScript or anything else that you happen to be using. I think that those are awesome technologies. And where I think that this fits in with this is if you're using TypeScript as an example, use this with your TypeScript. Use this to say, right now while I'm coding, I have the IntelliSense, I have the whatever reference material I wanted. But when you actually do your transpilation, your type information continues to carry along. You can come back later. If you have this library that's fully transpiled and minified, you can't look through it anymore. You now have a reference. Use it in concert with these technologies to make it better. So, in the end, types reveal intent. Type checking and annotations provide the insight into how a function behaves, what we mean, and it ensures that we continue to treat it the way that it was originally intended. So, when the going gets tough, the tough use types. Do we have a little time for questions? A few minutes, a couple minutes? Okay. I wanted to really zip through because this normally it fits into a little longer time slot. But anybody have any questions?
Yeah. Is it always type checked at runtime?
Currently, the library only supports runtime checking. Yes.
Okay. That seems that would add an overlay.
It does. It's about 40 microseconds. So it doesn't cost you much, and especially, when I'm actually doing my performance testing, I run checks on about 1,000 functions, so that way I can actually make sure that I'm getting something resembling a good average. So yeah, it does. It adds just a hair. Anybody else?
Have you talked to the transpiler people to see if they could put your stuff into the output so that at runtime it is being checked?
What happened to me? Okay. So the library itself is actually only about 6 weeks old. So still kind of new. There are people that are using it, and I've been using it on my personal projects. I've been trying to kind of get it worked into the stuff at work, but it's something where it's just so new that I haven't gotten a chance to really kind of reach out. So, anybody else? I saw kind of a half hand. No? Okay. Well, then thank you. I'm Chris Stead. Feel free to reach out to me at any time. If you do have questions in the future, please hit me up. I'm always available.